All right, on to the introduction. Data mining researchers often use classifiers to identify important classes of objects within a data repository. Classification is particularly useful when a database contains examples that can be used as the basis for future decision-making. For example, for assessing credit risks, for medical diagnosis, or for scientific data analysis. Researchers have a range of different types of classification algorithms at their disposal, including nearest neighbor methods, and he lists a few more. Over the years, many variations of these algorithms have been developed, and many studies have been produced comparing their effectiveness on different data sets, both real and artificial. The productiveness of classification research in the past means that researchers today confront a problem in using those algorithms, namely, how does one choose which algorithm to use for a new problem? Now, I will point out here as an aside that this is a case of my use cases. This is an instance of a use cases for my NLP PICO proposal. You got a problem, you got a question. It's about picking an approach, and it's about classification. So the productiveness of classification research in the past means that researchers today confront a problem in using those algorithms. Namely, how does one choose which algorithm to use for a new problem? This paper addresses the methodology that one can use to answer this question and discusses how it has been addressed in the classification community. It also discusses some of the pitfalls that confront anyone trying to answer this question and demonstrates how misleading results can easily follow from a lack of attention to methodology. Below, I will use examples from the machine learning community which illustrate how careful one must be when using fast computational methods to mine a large database. These examples show that when one repeatedly searches a large database with powerful algorithms, it is all too easy to, quote unquote, find a phenomenon or pattern that looks impressive even when there is nothing to discover. So actually, it's important here, I think, that he's not actually talking about the idea that you can easily find one classification algorithm to be better than another, but rather what he's proposing here is that you can essentially find too easily find patterns in that data. So think about this as not finding correctly that one methodology for finding them is better than another, but rather accidentally finding things in the data that are spurious, that aren't really there. As he says, it is all too easy to, quote unquote, find a phenomenon or a pattern that looks impressive even when there's nothing to discover. All right, so going on from there, it is natural for experimental researchers to want to use real data to validate their systems. Culture is involved in the machine learning community that now insists on a convincing evaluation of new ideas, which very often takes the form of experimental testing. And certainly, as an aside, this is the case in our community in natural language processing. And looking at the history of the field, language processing was essential, was seminal in making this popular in computer science in general. So this idea of this culture of experimental testing, he says, this is a healthy development and it represents an important step in the maturation of the field. One indication of this maturation is the creation and maintenance of the UC Irvine repository of machine learning databases, which now contains over 100 data sets that have appeared in published work. This repository makes it very easy for machine learning researchers to compare new algorithms to previous work. The data mining field, although a newer area of research, is already evolving a methodology of its own to compare the effectiveness of different algorithms on large databases. Large public databases are becoming increasingly popular in many areas of science and technology, bringing with them great opportunities, but also technical dangers. As we will see below, however, I don't know why the word however is there. As we will see below, however, one must be very careful in the design of an experimental study using publicly available databases. Although the development and maintenance of data repositories has in general been positive, some research on classification algorithms has relied too heavily on the UCI repository and other shared data sets. And of course, as an aside, we have that problem in spades in natural language processing. We rely as a community very heavily on, I think, a relatively small set of shared data sets. Okay, although the development and maintenance of data repositories has in general been positive, some research on classification algorithms has relied too heavy on the UCI repository and other shared data sets and has consequently produced comparative studies whose results are, at best, confusing. To be more precise, it has become commonplace to take two or more classifiers and compare them on a random selection of data sets from the UCI repository. Let me just say today, you would probably say from Kaggle. It's an old paper from before the turn of the century. Any differences in classification accuracy that reach statistical significance, more on that below, are provided as supporting evidence of important differences between the algorithms. As argued below, many such comparisons are statistically invalid. The message to the data mining community is that one must be exceedingly careful when using powerful algorithms, to extract information from large databases because traditional statistical methods were not designed for this problem. Below, I give some examples of how to modify traditional statistics before using them in computational evaluations. So let's go over sort of what the situation is that Salzberg is sketching out for us. So he is writing from a time when evaluations on shared data sets had become pretty common. People were using them quite often to compare different classification approaches. And then if they had differences in accuracy that were statistically significant, and we wish we did that much significance testing, right? Then that was argued to support the idea that there were important differences between the algorithms. And he's going to make the point as we go on that if you use techniques over and over on big data sets, eventually you're going to find a statistically significant difference. And he's going to argue for this and argue for a solution from statistics and from valid and invalid hypothesis testing.